This is Steve Hall. One more warm-up call. We will be firing it up. I see we've got a couple customers already waiting for the material properties session, the Ag Engineering Review. We'll be with you in just a few minutes, and we'll start right about at the turn of the hour. See you soon. Looking forward to a good meeting review tonight. Thanks. Okay. Welcome to the Ag PE Review for 2/16 of 2016, February 16. We are going to take a look at material properties tonight. See, we've got several people on the line. You are welcome to introduce yourselves. See if we've got two-way communications here. I'm seeing about 10 people up right now. Chad, Daniel, Dennis, Derek, Gary, Gloria, John, Justin, Laura, Mark, P. DiMaggio, Stephanie, and Tarzan. All right, great. Welcome. Glad you're here. We are focusing on materials tonight. So we'll go ahead and just launch into this. I am Steve Hall, professor at Louisiana State University. I am focusing on materials tonight. We are connecting in with a number of the components, most of them under Section 3, a couple of them under Section 1. And we'll review some of those. 2016 is the second year of the new exam, so I'm walking through this. You can see it on your screen. There is some overlap with the old exam, and there's some new material. Preparation is important, so congratulations to each of you for being here. Good job. I presume that also means you've probably listened to or seen some of the other ones as well. So good job, and keep at it. I'm going to make some preparation suggestions, and then we're going to move on to actually the specifics on some questions that you might see on the test. So first of all, you're doing exam prep. Ideally, give yourself a fair amount of time, 3 to 6 months. We're probably only about 2 months out now from this spring's exam, but hopefully you've been at it for a little bit. I strongly suggest you have particular times and then even specific things. You don't have to do exactly what I suggest, but simply the idea of a regular every week or certain days that you're going to do your review. So these are some of the suggestions. First of all, find a location. Location, location, location. That's what they say in real estate. Not a bad thing when you're studying. Find a place away from distractions that's quiet, something that is your space. Could be the kitchen table, except if all the kids are around, then that might not be your spot. It might be in the office, someplace where maybe you can close the door, someplace you can be comfortable. I say have a little water to drink, but for you that might be a cup of tea or something else. And also space to work. You're going to work problems, so I want you to find a place where you can spread out a little bit, have your resources, and then do this regularly. My own personal time was 6 to 9 p.m. I set this Monday to Thursday, so I was doing 12 hours per week for 3 months. I had a table in my room. It was a certain space, and even one end of the table that was my favorite spot. I actually ate and drank a little bit while I was eating, and then worked problems. I had a box of books, and you can add or subtract references as you see fit, but your job is to have not just as many books as you can carry, but books that you know where to find the answers in those books. So books you're comfortable with, books you work the problems with. This webinar series covers a bit. You can also look through the NCEES, National Council on Engineering Examiners, and there is the PE exam info there. And then the Bio and Ag 2015 upload is at that lower website. So you can check on those, see what the specifics are if you haven't already looked through that. So some of the particulars, these are the sort of large areas. First one is system applications. This is everything from pumps, energy conversion, graphics, safety, stress and strain. That's number one. Number 2, natural resources and ecology. So there's sort of the bio or environmental side, ecology, erosion, irrigation, nutrients, soil and water, things like that. The third one is process engineering, and that includes kinetics, transport, properties, biomaterials properties, which we're going to talk about tonight, reactors, mass balances. Number 4 is facilities, and this can include structural components. This can include animal or plant, for example, greenhouses or particular animal facilities. And number 5 is machines. All kinds of questions about power, motors, engines, components, mechanical components or models of those. So those are kind of the general areas. We're going to focus on number 3 tonight. And again, what I suggest is find the things that make sense to you and get good at them. Try to at least cover the other areas somewhat, as much as you sort of reasonably can. But I would really strongly say get really good at some of them. So then you can really tackle those and get at least exposed to the other ones. So get a little bit of breadth, but then get really good at some of them, especially the ones that sort of reappear. There's questions in all 5 of those that have something to do, for example, with energy or resources. So you're going to see those types of questions again and again. And then things where you're really just, this does not make sense, then skip it. Don't worry about it. Move on to things that actually make sense and get good at them. Okay? You can use any references you want. The FE review manual, so the FE, not the PE, but the FE, that is the basics. I actually really like that as a reference. It's very basic, but it covers the bases. Textbooks that are relevant to the various areas, those can be very useful. ASABE references can be very useful, and I'm going to mention a couple of those tonight. And then you need to know where in the textbook, where in the reference you can find the answers. And so mark them. You can put little tabs in there or whatever and use them so you can find them. And you're probably going to have some favorites. You know, I actually thought that the FE review manual for me was one of my favorites. And then there were a few other books. There was a thermo book I really loved. There were some other books that, you know, just seemed to have the answers I was looking for. And I kept those right near the top. And then you can have some other stuff for backups. If you get in a pinch, you can look at those. But probably you're going to want a limited number of references that you know very well. And again, friends, colleagues, family, tell them what you're doing. This is a big deal. Smart people study a long time to pass this exam. And sometimes you don't pass it the first time. I hope you will all pass it. But get your family to understand you need this time to really focus on this. And then promise them, okay, when I'm done with this, I'm back, we're going to have fun together, you know, and I would really hope that you would study hard, take it once, and pass it. So here's a kind of warped story. We were settling into an exam when I took it years ago, and somebody behind me says, "What time is it for you?" And one guy says, "Oh, it's," and I'm looking at my watch, you know, and the other guy says, "Oh, it's my 4th time." The other guy says, "It's my 5th time." I'm like, "You've taken this 5 times? Where do you work?" At the nuclear plant. A little scary, so I would suggest study hard, take the test once, and get it done. I also had some other general suggestions. When you take the exam, make sure, by the time you've done that, studying one more night or one more day is not going to do it on that last day before the exam. The last day before the exam, get everything organized, relax, do something fun, don't get too crazy, get a good night's sleep, wake up early, have a good breakfast or a cup of coffee, whatever it is that helps you to get going, feel good, get to the exam site, be comfortable there, and just do a good job to focus on the exam. So those are my suggestions. Again, here are the particular focus areas that we're going to work on tonight. This is materials. Ag and biomaterials. We're going to talk about 3E, which is physical and chemical properties of biological materials. We're going to have a bit of overlap with 3D, mass transfer between phases. So a lot of times when things change from a liquid to a solid or a liquid to a gas or vice versa. Psychrometrics, 3I, overlapped with that. That's water, oftentimes changing from a liquid to a solid or a liquid to a gas, typically. Energy transfer, especially latent heat and phase change, that's number 1, L. And mass balances, number 3, J. So we're going to do a bit of all of those, but the main focus is really biomaterials. And here are some of my references. So the upper left, engineering properties. This is an ag engineering ASAPE publication. At the top is NCEES, the fundamentals of engineering, the FE. That's actually online. You can get it. On the right is a physical copy of it. At the lower right is the old Mosinine book, Thermal Properties of Food and Ag Materials. And on the lower left is Park and Lake's Biomaterials, an introduction. That's more bio rather than ag, but each and all of those and others can be helpful. I've also mentioned this listing that includes Rheology and Data's Engineering Properties of Foods book, Merva 1995, so that's getting a little old now, but Physical Properties of the Plant Biosystem, Reynolds and Richards Unit Operations, and again, there are more recent versions of some of these. Feel free to avail yourself of those, but find things that are useful for you. We also have a number of standards, and these standards are available at the website shown at the bottom. That's Hellevaang, and or available through the ASAPE standards area. D241.4, density, specific gravity, and mass moisture relationships with grain. D243E, thermal properties. D245.5, moisture relationships. That's plant and ag products, how they absorb or lose moisture. EP545, loads. So if you have grain in shallow storage structures, how much force will they put on the walls? And then Hellevaang, temporary grain storage, that also has to do with grain and forces that provide. So these are, again, some suggestions for areas that you can study or use as references. We're going to talk about a number of topics, and then we're going to try to get into some specific problems. So rheology. Rheology is essentially the properties, a description of the properties of materials. Density, how heavy, how dense things are, specific gravity, the inverse of that. Moisture content. Thermal properties, how do things heat or cool, how well do they hold thermal energy, and loads on structures, especially from grain or flowing products. It could be also things like granular products, sand, or other types of granular products, fertilizers, that sort of thing. And then we're going to have a little bit on psychrometrics at the end. So rheology is the study of deformation and flow of matter. And so it is simply what happens to materials as they are subjected to forces and flows. And of course, it's very interesting in biomaterials. So at the atomic level, we've got something where when you squeeze two atoms together, you see that compression in the lower left, there are more forces that actually want to push them apart. Conversely, as you pull them apart, there is a force that is trying to pull them back together. We call that tension. Now we get far enough apart, and at the atomic level, when you get things far apart, they actually do not interact very well with each other. At the macro level, that can actually result in failure, where things actually pull apart and then they don't go back together very well. In the lower right, I have the standard stress-strain diagram of typical linear materials. This would apply to typical metals, steels, things like that, where there's a single E, and E is just a slope of that stress-strain diagram. We are going to look at a variety of materials where, again, on that left-hand side, we have Hookean materials, these sort of linear elastic materials, oftentimes things like metals in standard macro type applications. We also have non-Hookean, so just next to the Hookean on the left-hand side, still elastic, they still stretch, but they have a hysteresis loop. When they come back, they don't come back by the same route. And they, of course, will lose energy when they do that. They'll tend to heat up in doing that. But they can return to something close to their starting point. We can also have a variety of inelastic materials that when you compress them or when you force them, there is a deformation and it is no longer elastic. It doesn't come back to where it was. Viscoelastic will stretch, and then you have a thing called creep, just a slow relaxation. Or viscoplastic just keeps stretching, and it's kind of like something halfway between a solid and a liquid. On the right-hand side, we've got liquids, and again, there's a variety of liquids. The far right is your classic Newtonian fluid, where as you stretch it, there is a force that is opposed to it, and it is linear. But you can also have, again, other non-Newtonian types of viscous materials. So the non-Newtonian that's shown at the bottom, again, has a hysteresis loop where, yes, you can flow it back, but it won't flow back quite the same as what it did. And then we have plastic. So viscous things are going to resist, but they will flow. Plastic things will flow, and then they actually require a certain amount of force before they'll move at all. So Newtonian fluids, even at a very low shear, they will flow. Bingham or plastic type materials actually resist flow. So these are things that actually might be like physical plastics, or they might be biomaterials that you have to pull on a little bit before they start to stretch. And then they will stretch, perhaps in a linear way in the Bingham, or perhaps in a somewhat nonlinear hysteresis type way in the non-Bingham materials. This is just sort of describing, wow, there's a lot of different materials, different ways of trying to describe what the materials really do. So again, back at the Hookean kind of classic materials that just simply have a linear stress-strain relationship, we have stress versus strain. Stress is force per area, and strain is stretch compared to the original, delta L over L. So these are sort of the classic definitions. And normal stress at the top there is simply the force normal to the area. Shear stress is where you are shearing something, so it is the force parallel to the area divided by the area that is in shear. It's a slightly different variation, but still it is force per area is stress. And typically it is still linear with the strain that's being applied, the stretch, the deformation. And at least for some reasonable distance, these are linear. They will stretch, and then they will return to a less stretched formation. Young's modulus is the definition. The slope of that line is E. Sigma equals E times the strain. Stress equals E times the strain. Or E is just stress over strain. Good night. We're still with you. All right. And for a bar, that delta, the deformation, is simply FL over AE. It's the force times the length divided by the area and divided by the E. So for specific materials and particular geometries, you can come up with very specific solvable equations. And these are some of the standards. Here again, we're going to look a little more closely at these stress-strain curves. Again, an elastic material is just something that you put stress on it, it will stretch. You let off on the stress, it will come back, it will stretch back, it will shrink back to the location it was previously. To the upper right, we have an elastic plastic. It's elastic for a ways, but if you go further than the first tilted line, you actually start stretching it, and it won't go back, and it will deform permanently. It will go back typically parallel to the elastic, so it remains elastic, except it has permanently deformed by the amount that it goes across. Lower left, you have something that's plastic. It is elastic for a period of time, then it deforms going across, And then it actually doesn't elastically go back. It simply, even though you take the stress off, it just stays where it is. And then we have lower right viscoelastic, something where you put more force on. It's a nonlinear response, but still you put more force, you will get more stretch. You put more stress, you'll get more strain. And when you take that stress off, it will return to close to where it started, but in a nonlinear way, in this way that has hysteresis. So those are some of the models, descriptions to try to help us understand these. Now I want to actually look at some real materials. So first of all, steel versus rubber. So steel is the steep one on this curve, and in fact it may be even more steep than that. And you notice that it's quite linear over that range that it has. Rubber, on the other hand, does not take nearly as much force to make it stretch, and we all sort of know that. Yank on a steel rod that is a 1/4 inch across, and you're not going to stretch it much. Yank on a bungee cord, and you can stretch it pretty well. The other thing that you'll notice is that the rubber is somewhat less linear, and I will also suggest it's actually somewhat less elastic. But it's somewhat nonlinear. It tends to deform at a lower force. On the other hand, it can strain a long ways. It can deform a long ways without failing. Whereas if you do manage to be a really strong person and stretch that steel very far, you may well succeed in breaking it or permanently deforming it. Whereas you can stretch that bungee cord quite a ways, you let off on it, and it comes back pretty close to where it was. So just interesting comparisons of typical, and rubber is in some ways a somewhat normal, or at least one proto-example of a biomaterial versus a traditional material. And again, the E is pretty constant over most of that area for steel. So you have a single E that's defined. It's a bit harder to define an E. It's more like the whole curve for the rubber. And here's maybe part of the reason that many of our biomaterials are actually created from a variety of micro and macro structures. So here's an example of hair. You actually have proteins at the level of the alpha helix and the protofibril, and then micro and macrofibrils, and then all the way up to the cellular level, and then the hair itself is actually composed of many, many cells. So you have these biological subcomponents that have their own properties. Some of those properties are going to come out in the macro property of a hair. How stretchy is a hair? How strong is a hair? And those will often be linked to the material properties. Here is a hysteresis cycle for a typical rubber. And what we see here is, first of all, there is hysteresis. In other words, it does not, when you stretch it, then when you let go of it, it does not come back to its original location in the same way that it went up. And then the other thing that we're seeing is that over time, you will permanently deform some of these materials, and they will have different hysteresis curves, and they may well slowly deform over time with many, many cycles. I want to talk about true stress and conventional stress. That's actually a definitional thing that could potentially be on an exam. And this typically will apply to more conventional materials. It might be steels. It could be biomaterials with somewhat more conventional properties, things like bones, where you actually have a fairly conventional type, fairly elastic component. That first part of the curve is fairly linear. And remember, the slope of the curve at the beginning, in that straight part, is E, stress versus strain. As you stretch these, you will get a necking, a thinning of the material. It's stretched. And this is especially true with biomaterials. It is true in steels, and it's called necking, and the steel will, provided that it is not too brittle, if it's ductile, it will stretch and it will get smaller. And it will essentially stretch, but it's getting thinner. that means that the area that the force is applied is actually getting smaller. So force per area, if you make the denominator bigger, or rather if you make the denominator smaller, force per area is getting smaller as it gets stretched. So make the area smaller, that makes the force per area bigger, makes the stress bigger. That is that true stress curve, and it actually goes up. Materials often have a thing called strain hardening. They actually get stronger, even though they're getting skinnier, they get stronger. Whereas conventional stress is just simply the force divided by the original area. But oftentimes the area changes over time. In biomaterials, the area almost always changes over time. Any significant stretch will change, for example, the area of a rubber band, but it could also be the area of a muscle, a strand of hair, a tendon, or some other component. So these will change, and so you want to be very careful if there are questions of this sort. What is the definition? Force per area, and is it force divided by the original area, or is it force divided by the actual area? And if it is force, if you're looking for true stress, it's force divided by actual area. If you're looking for simply conventional stress, force divided by the original area. So remember, this is what we saw previously on the stress strain. Stress is just force per area. It's just that you have to define what is that area. And again, similar with strain. Strain is just delta L divided by L0, but you need to know what are those changes. So let's do some examples. All right, here's our first example. A steel bar with known dimensions is subjected to an axial compressive load. So this is a bar in compression. Now let's talk through this a little bit. You want to approach problems in a consistent way on this exam. So you are at your location, you have your piece of paper, you're starting to write some notes. It is subjected to an axial compressive load. You've got a picture. Here's a rectangular bar, and your arrows should be pointing in for the compressive load. It's getting squashed. The modulus of elasticity and Poisson's ratio are known. So modulus of elasticity, E. Poisson's ratio, nu, which is the ratio between the compression and the expansion as it compresses. What is the final thickness of the bar? And they give us some numbers. Now, first of all, should the bar be fatter or skinnier? That's kind of one first thought. Well, you're compressing it, you're squashing it. I think the bar is going to get thicker. So if it starts at 20, it should be more than 20. So let's crunch some numbers here. But I'm going to likely cross out A and B right away. No, it should not get skinnier. It should get thicker. So maybe it's C, and probably it's D. Not all the questions are going to be quite that easy. So here's a axial tensile load. A little bit different question. Now we're pulling on it. Now we've got some numbers to work with. Steel bar subjected to an axial tensile load, 250 kilonewtons. Modulus of elasticity is 200 gigapascals. So we've got E. Poisson's ratio is 0.3. What is the final thickness of the bar? Now this time, our bar is 20 millimeters across, 100 millimeters high. Again, let's first of all think, is it going to get thicker or thinner? This time it's in tension. It's getting stretched. It's going to get skinnier. It's going to get thinner. That 20 millimeters is going to be less than 20 millimeters by the time we're done. So let's go ahead and put our numbers down. E is 200 and gigapascals. Keep our units. Nu is 0.3. Since that is strain per strain, it is dimensionless. Keep your dimensions. Be careful as you do these problems. Remember, delta equals PL over AE. Delta axial is PL over AE. Force, 250. It's kilonewtons, 250 times 10 to the third newtons. L, 0.5 meters. 500 millimeters is 0.5 meters. Be careful with units. And then we've got on the bottom A, so cross-sectional area, 20 millimeters 0.02 meters, 100 meters tall, 100 millimeters tall, 0.1 meters tall, and then we've got our E, 200 gigapascals, that's 200 times 10 to the 9th pascals. All right, so we've got, crunch our numbers, 0.0003 meters or 0.3 millimeters. That is how much deformation we've got. Okay, that's not the answer though. What is the final thickness? Okay, so the final length of the bar is 500 millimeters stretched plus 0.3 millimeters. Okay, so we're stretching it just a little bit. We are stretching it a little bit. Our E axial, our strain, is delta over L. It is the change over the original L. 0.003 meters over 0.5 meters. Meters over meters. Should be unitless. 0.006 meters per meters or unitless. And remember that nu is the strain in the lateral direction divided by the strain in the axial direction. So now we have the strain in the axial direction, and we have nu, 0.3. So the strain in the lateral direction is simply those numbers multiplied together. And now it's 0.0002. So that is the strain. Still not quite the answer. So watch, what is the answer? What is the final thickness of the bar? Now definitely we're going to use that 0.002. Final thickness is 0.002 times the original thickness. The original thickness was only 0.02. So we are at something like 3.75 times 10 to the minus 6 meters, 0.0038 or 0.004 millimeters. That is the change in thickness. Again, what is the final thickness? Is it getting fatter or thinner? It's getting thinner, 19.996 millimeters. Okay, so several steps here. Organize. Keep yourself in a very organized fashion. Keep track of things and watch what's happening, and then continue to go back to the question until you get the right answer. Here's another one. Block of cheese. This is a food materials type emphasis. Block of cheese with known dimensions is stacked and subjected to an axial compressive load. I haven't put the numbers in here, but this again is sort of a thought problem. You're stacking cheese. So, okay, you oftentimes need to stack food materials. It is subjected to an axial compressive load. Okay, so they're stacked up and they're being compressed, perhaps by their own weight or maybe by the weight of something else. The modulus of elasticity and Poisson's ratio are known. This is just like the steel, except something tells me the properties will be different. What is the final thickness of the sample? First of all, is it going to get thicker or is it going to get thinner? I think it's going to get thinner. We're squashing it down. So that's the first thing. Now let's put some numbers to this. Here we have a compression from stacking. Again, we have some kind of delta. The delta is FL over AE. Same type of thing. What are our areas? What are our forces? So the force is that compressive force. The L, in this case, is the length, quote-unquote length, but the length is like the height of cheese. So it is the H that we have, whatever number that is. And then what is the area? It is the L times the W. So and that's the cross-sectional area of the cheese, defined there at the top. And so that is our cross-sectional area. And then E. We need E. And hopefully we find that somewhere, okay? So we've got a delta. That's a function of F, H, L, W, and E. Meantime, the axial strain is delta over the original height, in this case, okay? So delta over H, or FH over L times W times E, all that's delta divided by H. And our Poisson's ratio, again, is lateral strain over axial strain. So the cheese will get shorter by delta. So if we want to know what is the new height of the cheese, it is H minus delta. Plug in our numbers. And it will get wider by that lateral number times the nu there. Okay. Now, the other thing, this other twist we've got is that E might or might not be linear for cheese. And cheese may have some other weird properties, like creep. Cheese can slowly compress. In other words, this is not necessarily a truly elastic material. This may have other viscoelastic properties. So if we know about those, and oftentimes those may be given or we may have access to those, then we may need to take those into account. So again, here's kind of this idea. A true Hooke's modulus type material, a steel, will look like the upper left, stress versus strain. It's linear. It's kind of like a spring. Stretch it out, let go of it, it comes back. A true Newtonian liquid will look like the upper right. You pull on it, it just keeps going. You stop pulling on it, it stops going. You pull on it some more, it goes further. It flows whenever there is a force on it. It stops flowing when there's no force. And then you have combination models. Lower left is a Kelvin model. It's really a Newtonian liquid type model, dash pot, in parallel with a spring. And it stretches, so it has a spring aspect, but it also deforms. Meantime, on the other side, lower right, we have a Maxwell type model where we have a spring aspect coupled in series with a flow type. So we've got a Hookean and a Newtonian combination that are linear. And depending on how fast you're pulling on this, you may get different stress-strain curves. So first of all, that last one is nonlinear, but it also can vary depending on how quickly you apply stress. In other words, what is the strain rate, that E dot? If you've got a slow strain rate, you'll get one curve. If you get a faster strain rate, you'll get a different curve. So nonlinear and affected by strain rate. So a lot of materials are a little bit trickier. Here's a plot of cheddar cheese with a certain applied force, and it is strain over time. So this is not stress strain. So look at this curve, strain in inches per inches. So it's sort of how much it is stretching on the vertical axis. Horizontal axis is time. And what's happening is that it is stretching a fair amount at first, and then it slows down, but it continues to, and this may be compression, continues to have a slow compression. And the slope of that curve is not linear. It is some function that has a function of t and functions related to the force that's being applied. And is it viscoplastic or viscoelastic? You could argue that it looks a little more viscoplastic, but it also starts from somewhat up. You have to put a certain amount of force on it to get it to deform, and then it deforms fairly quickly and slows down over time. So we have some interesting behavior, and this is called creep, that things that have force on them over time will slowly deform. This applies to a wide variety of biological materials. It can occur in work aspect where people's backs will get strained over time. You're actually literally stretching things out. You can have compression, standing up all day. Literally the discs of the back are compressing over time. Now at night you may have the reverse process where you lie down and they are slowly stretching back out. The same thing for many types of food products as they get stacked. You may have similar types of properties that respond over time. At a huge scale, glaciers have creep. Glaciers actually flow. Now they're ice, which is a solid, but it is ice that over time, over years, maybe decades or centuries, slowly ice flows down the mountain. That is creep. All right, so here's another sample problem. Sample problems can't get too crazy, but they can ask you to address some of these types of properties. A block of cheese with known dimensions is stacked, subjected to an axial compressive load. After being stacked for a period of time, 2 hours, what is the final thickness of the sample? Now we've got a time component. We need to go and find one of these graphs with the time aspect on it. So we'll use that same graph. We go 2 hours over, 120 minutes. What is the strain? It's approximately 0.09, okay? And you got to be a little careful because will the mathematical model that describes that slope still be good further out? Use your head, stay smart. Original dimensions, 100 by 100 by 100 millimeters. Okay, just a square block, cubic block. Strain, 0.09 mil per millimeter. Okay, that is our strain from the graph. So 100 minus that little bit of compression. What's interesting, this is a whole lot more than what the steel compressed. This has actually gone down 9 millimeters. It's gone down a fair amount in a couple of hours. Now, it's also going to expand. And if Poisson's ratio was given to us as 0.3, then there will be an expansion. And again, that is proportional to the strain in the other direction. So we're going to have 0.3 times the 0.09, or 0.03 millimeters. So it's getting wider by that amount. So we're going to have 103 by 103 millimeters, getting fatter, but it's 91 millimeters down. Okay. Derek's got a question, so we'll see if we can take that. Let me take a quick look. See what we've got. Should the problem say final thickness after 2 minutes? Yes, thank you. 120, yeah, very good. 2 minutes, thank you very much. Yeah, so watch your units. My apologies on that. Thank you, Derek. So we correct that. So that time, nevertheless, the time is actually an important component of what we're doing. So yes, thank you very much. 120 seconds. We can have a similar process as stress is applied, a known force is applied, or a known compression is applied. So if we squeeze something a certain amount and then stop squeezing it, we just sort of leave it there, it will slowly adjust to that. Lots of biomaterials, lots of these viscoelastic materials will adjust, and the stress slowly reduces. Now again, it's nonlinear. So here is a stress relaxation curve for potato tissue. Stress in PSI, you squeeze it a certain amount. This sample had a certain size, 21.8 millimeters in diameter, 26.9 millimeters in height. You can think about what that size is, but it's a chunk of potato material. Compress it a certain physical amount and then wait. And slowly the stress in that is being reduced. It's adjusting to that force. So this is called stress relaxation. And again, it has a time component. So these nonlinear aspects, where we've got a stress strain or a strain time curve, wherever we have something that's nonlinear, how do we decide, how do we linearize this? So here's a typical example. This is an actual stress strain curve for a particular biomaterial. Stress in megapascals, strain in unitless millimeters per millimeter. And you can see that it is quite nonlinear. We have 3 possible options. Maybe there's more options, but 3 sort of standard options. The first is simply to connect the origin to the final point. Draw a straight line. Well, that's about E. That's sort of, just ignore all the stuff that's nonlinear. That's E. And so that is the chord, the origin to final point chord. You can see the real process is quite nonlinear and has hysteresis. Goes up one way, comes down a different way. But one option is to simply connect the origin and the final point and call that E. Another is to connect to some point on it. Okay, so that could be a secant type method. A third is to, at a particular location of either stress or strain, to draw a tangent. So at that moment, that tangent, at the moment that it's drawn, is C. That's the E value. The slope of that line is the E value at that moment. Now, if you go a little further out on the strain or a little further up on the stress, that's going to change. The slope of that is going to change over time. At some point, it may be the same as the B slope, or at another time, it'll be the same as the A slope. But that is changing over time. So this is simply ways to linearize, but it's also reminding us that this is not linear. And to really account for this, sometimes we may linearize, sometimes we may acknowledge that this is nonlinear. We also can think about what happens in terms of the energy in the material in these nonlinear type applications. So this is a sample of a food product, actually a potato cylinder under certain conditions, and it's a stress-strain curve. Interestingly, as the force is applied, we get a moderately linear, it's not perfectly linear, but it's fairly linear going up to this top point. The E value, again, is probably much, much less than, that slope is much lower than it would be for, let's say, a similar size piece of steel, but nevertheless, it's fairly linear going up. Notice that it comes back down in a very different fashion. This is hysteresis, and so the little cross-hatched area describes hysteresis. That is essentially some energy that is lost, okay? There's another component of this, which is the remaining energy under that curve, the remaining area under that curve, and that is called resilience. So strain energy density is all of the area under the curve. That is the strain energy density. This is one more definition and one more reminder of what information we might have off one of these curves. All right, I'm going to take a little break. I think you can take a little break, and we'll come back. Let's say 2 to 3 minutes. Get up, stretch, get a drink of water, whatever you got to do, and we'll be back in short order. Recording. Okay, welcome back. We will continue from this slide. We've been talking about biomaterials, and we've worked a few problems. We've talked a little bit about how to handle the problems and how to study, but also how on the test to try to keep things very organized so that we get the best results. We're going to move on and talk specifically about rheological behavior of fluids. So here we are starting with Newtonian fluids. A perfect Newtonian fluid, as you apply shear it responds linearly to that shear rate. So you get, again, a straight line on a shear stress versus shear rate, a tau xy versus dv dy type plot. Then there are a variety of other types of materials. Higher up on the curve, we have a plastic material. This could have a similar slope, but unlike a Newtonian fluid, with the Newtonian, as soon as you apply some shear, as soon as you apply some stress, it will start flowing. Even just a little bit, and it'll flow a little bit. With a plastic material, if you don't apply enough force, it won't move at all. Once it gets moving, it will stretch. So that's a plastic material. We also have the Casson type plastic at the top, which is then a nonlinear. As you apply faster shear, you have a nonlinear response to that. Down in the Newtonian, we have some other types of fluids. They're not plastic in the sense that they don't resist force. They still flow. As soon as you start applying a force, they will shear. But one of them is a pseudoplastic in that it goes up before it goes over. One is a dilatant that goes over before it goes up. So again, we have these different nonlinear types of fluids, as well as sort of the classic linear Newtonian fluid. So here's a possible way of looking at shear modulus and viscosity, kind of a little block, an imaginary block of a fluid. You put a shear force on it and it deforms. Now what we're looking at the bottom is perhaps, let's say, the edge of the wall of a pipe, the bottom of a ditch, something that is fixed, so that that shear is simply making part of the fluid move, but the fixation to the wall is making part of the fluid try to stay in one place. And so what you get is a deformation. So a lot of times we'll have fluid flow that is not consistent across a pipe. It will go much slower near the edges and much faster in the middle. Here again is a little more information on what are the material properties for fluids. So viscosity is essentially the resistance to flow. And here again we have a thing that's essentially a sort of force per area. Now it's tau, okay, and tau is proportional to dv dy, okay, the shear by way of mu. So that is the sort of classic viscosity. And then there's another version of viscosity that is simply the viscosity proportional to the density. So kinematic viscosity is standard viscosity mu divided by rho, the density. Pretty straightforward. And the viscosity units are in poise. Okay, 1 poise is 0.1 Pascal seconds. Okay, which is also, what is a Pascal? Kilogram per meter second, kilograms per meter per second. So a poise is, in fact, a Newton second per meter squared. Okay, you can kind of look at those units a little bit. But typical viscosity units are in poise. Okay, and we're going to have, or in Pascal seconds, just like we talked about at the bottom. So here is a series of viscosity values for a variety of liquids, agricultural type liquids, apple juice, corn syrup, cream, honey. You know that's going to be a higher viscosity. Tested at different temperatures. Why does the temperature matter? You got it. Slow as molasses in January. Well, what's January got to do with it? It's cold. Okay, so when it's cold, the viscosity will tend to be higher. So these are typically tested at some kind of a standard laboratory type test. And then the viscosity is in Pascal seconds. And you can see that apple juice is quite thin, 0.0021, quite a low number. Another test, the Brix, so a higher Brix is a higher sugar content. So it is indeed a sort of thicker. As you add more solids, you tend to get a higher viscosity. Both tested at 27 degrees. One of them is about 10 times more viscous. The high sugar, the 60 Brix, has more sugar than the 20 Brix, and it is more viscous. Honey is, on that same scale, almost 5. So 2 more orders of magnitude in addition, thicker, more viscous. Okay, and a variety of other numbers for cream, oil, milk. You can see what those numbers are. Again, this whole idea that temperature has an effect, a big effect, okay, and it may be an Arrhenius type relationship, okay. Mu is the viscosity in pascals seconds, and that may be compared to some kind of base mu constant times the exponential of EA, some kind of activation energy, and divided by RT. R is the gas constant and T is the absolute temperature. So again, in using this, you got to put temperatures into Kelvin, not C. You got to make sure you remember, put them into Kelvin. And again, the R also is kilocalories per gram mole degree Kelvin for this particular one. Time-dependent fluids. So like we had time-dependent solids, we also have time-dependent fluids. So the apparent viscosity may be a function over time. On the top we have something where the apparent viscosity does not change over time. As you apply more force or as you wait for something to happen, many fluids are relatively time independent. They continue to have a similar type of response to viscosity over time. But some materials can be rheopectic, okay? It is becoming thicker as time goes on. So some materials, as you apply a shear, they resist it more. You can think about what materials those are. And other materials are called thixotropic, and they actually, as you apply more shear or more vibration, they actually will get thinner. And concrete is an example. And actually, ice or snow in avalanches would be another example. As it's moving, it flows. But if you are captured in an avalanche, it's a terrible thing. Just like if you're captured in concrete, it gets thick and heavy and hard very quickly if you cannot apply a strong shear stress. And again, down at the bottom, we've got some, again, a sort of standard curve, shear stress versus shear rate. Neither one of these is going to be linear, and they also have different hysteresis type curves as they go up or go down. So again, there can be a time-dependent aspect to the viscosity of fluids. So now let's also talk about, while we're talking about fluids, now we put fluids into things. Okay, so fluids, the effect of water potential and strain rate for, in this case, it's apple. Okay, what is the stress strain? So now we're back to a solid, seemingly a solid piece of apple, but now it's the solid that has more or less water or more or less of a mannitol solution, more or less of some liquid, and it changes the stress strain curves, and it changes them a fair amount. Now you also notice that they have also done these tests at 2 different strain rates, 0.4 per minute and 1 per minute, so a faster and a slower strain rate. And they get different results based on how the strain is applied, but also based on how much moisture is in the product. Another property that is kind of like flow, but a bit different, is bulk density. Okay, so a property of particulate materials like sand or grain, could also be fertilizers, anything that is granular can have this bulk density, okay? And it is the mass of all those particles divided by volume. So it's a kind of density, but it is not the density of an individual particle. It is a density of the collection of particles. So when you have a bin full of grain, a bucket full of grain, a bag full of grain, they occupy some volume. And so it's simply the mass divided by the volume, kilograms per cubic meter. The volume then does include the pore space. Okay, that's the area between the particles. So, and that is typical applications, that's filled with air. So there is some mass in there, but that mass is probably about 2 to 3 orders of magnitude less dense than the material itself. So it's a lot less dense. So most of the bulk density is simply based on the mass of the grain or the sand or the other granular material. A little bit fuzzy here, but here are some fluid properties from the D241.4 standard. This is the ASABE or ASAE originally standard for mass-moisture relationships of grain for storage. Bulk density, and for alfalfa, barley, beans, on down, peanuts, popcorn, all kinds of things. What is the kilograms per cubic meter or pounds per bushel? Okay, again, your units may shift, but you've got some idea of how dense these are in terms of as a bulk, as a collection of alfalfa seeds. What is the typical density? And you'll notice what is the density in kilograms per cubic meter of water. Should be about 1,000, right? So most of these materials are a little bit lighter or a fair bit lighter than water. So 700 is 2/3 of water. 300 or 400 is maybe less than half of water. So depending on what they are, they could be fairly dense, nearly as dense as water, or they might be a fair bit less dense. Specific gravity and percentage of voids in bulk grain, again from that same standard. And here we have, for example, barley, a certain variety, at a known moisture content, and the airspace in the bulk. Okay, how much is air, how much is kernels? And then here's the kernel specific gravity. So the specific gravity of a given kernel is 1.13. In other words, it's more dense than water. You drop that barley kernel into water, it will probably sink. And it looks like most of these things are actually kernel density heavy enough to sink in water. But collectively, their bulk density, because of those air spaces, tends to be less than the density, the net density, bulk density of water. Okay, and they do vary depending on the moisture content. So this is the other thing that we would need to test. We can also look at thermal properties of grain. 243.3, D243.3 is another ASAE standard. Here is a variety of materials that have been specified. Their known moisture content on a percent wet basis. So in other words, how much moisture divided by the total amount of mass. That's your moisture content. And they could be quite dry, 0.9, or they could have a fair bit of moisture. Down at lower in the table, we see we've got one that's 30% moisture content. They give us a temperature, and then they give us thermal properties. Specific heat, kilojoules per kilogram, degree Kelvin. Conductivity. Okay, this is a thermal energy movement parameter. Okay, watts per meter degree Kelvin. Diffusivity, thermal diffusivity in its units. And there are references for each of these. And again, there are tables of these that will give us these thermal properties of grain. So we've got all of these. One more. Again, these are different ASABE standards that are available to ASABE members, EP 545, loads exerted by free-flowing grain on shallow storage structures. And this may apply similarly to other granular structures. What we see there is an angle of repose. The angle phi is the natural angle that the grain will come to, provided that it has a straight, flat support underneath it, a typical concrete floor or something like that. And that angle of repose is a function of the material properties of the grain. We will also look at other forces. So if this flowing grain makes a pile and comes in contact with a wall, that will put some force on the wall. How much force is that? So how much force is on the floor? How much force is on the wall? These are things that you need to know if you are constructing a structure to keep this type of material. Okay. We've got some definitions from EP 545. The total equivalent grain height. The average grain height if the top grain surface is not horizontal. Okay. And again, you've got some angle of repose, but this is the height. Okay. Design approach. This is for shallow grain holding structures. What are the material properties of the material that will be stored in here? And you probably want to test this or run these calculations for each likely material that you expect to have in here. You'll need to know something about the bulk density, something about the material's angle of repose, and again, that can be different for materials that have more cohesion or that are slipperier, and that of course is tied into the coefficient of friction. Okay, we would then use the properties to calculate the total equivalent grain height. How high is that grain? And then what are the static pressures? What are the pressure at a particular point? And what are the static lateral pressures? And of course, vertical pressure on the floor. We got to make sure that that concrete is strong enough to hold this load that's being applied to it. So the concrete needs to be strong enough, and the walls need to be strong enough to handle this load that's being applied. We then calculate the resultant forces, and here is the definition. The force PH at a given H equals LH squared over 2. Pretty simple. L is the lateral pressure, and that is a function of depth Z. Okay, we see down below we've got a lateral pressure, and H is that equivalent grain height. So lateral pressure, L, okay, equals simply a K, this ratio of lateral to vertical pressure, times V, the vertical pressure, okay, at the grain depth Z, okay, in pounds per square foot, okay. And V equals W, Wg, where W is the bulk density, and we've seen that on a previous slide, in pounds per cubic feet, and G is simply gravity. Okay, so now we've sort of defined each of these terms. We can plug them back in. And here is that. It's a free reference. You can still get to it, or as of fairly recently, you could still get to it on the web. And this is a reference again. This is out of North Dakota State. Hellebang put this together a little while back. The pressure grain exerts per foot of depth is called equivalent fluid density. So is this a fluid? No. Does it act somewhat like a fluid? Yes. Okay, so flowing grains are somewhat like fluids and can be viewed like a fluid in some ways, especially this idea of pressure being put on a given part of a structure. And so we've got, again, some definitions for this equivalent fluid density, pounds per cubic foot. So it is a kind of density type measure, and there's different measures. Barley, wheat, they're going to be, relatively heavier. Corn, some of the other things may be lighter. Sunflower may be a bit lighter. Oat may be a bit lighter. Okay, so they're going to have less density. They're going to exert less force. Okay, and the particle size distribution. Okay, so that's, I guess we'll stop there. And but Hellebang would be something I would encourage you to review and try to work a couple problems related to that. Particle size distribution is simply another aspect of this. Okay, how many small, medium, and large particles are in a particular collection of particulate material. So things like soils, and also many ag and bio products will have different size distributions. They'll have some small material, they'll have some medium material, they'll have some larger material. One standard way of dealing with this can come from the CE, the Civil Engineering Manual, Chapter 35, and that's soil properties and testing. One of the most standard ways of testing any granular materials and looking at particle size distribution is sieving. So you have different sieve sizes with different openings, and typically you have the largest opening on the top, and you sieve that down to a smaller opening, sieve that down to a yet smaller opening, and look for the distribution. Things that are larger than the cross-sectional area of the opening, they will fall into that, and you can mask those or measure those. Same for the next size distribution. Smaller than the first one, but larger than the second one, those that stay in that second sieve, and on down through. And essentially it is a distribution. So we really have to think a little bit statistically. It's a particle size distribution. So we can go from something like soils, but we can also think even about something like nanoparticles. A lot of times there are distributions. They may be a normal distribution, they may not, okay? If they are approximately a normal distribution, then they may have a mean or average particle size. And then there may be some measure of the dispersion of particle size. So how much variation is there? A standard deviation would be a measure of the variation, the dispersion of particle size. So here again, a little bit of thought process. Perhaps in the upper distribution, we have a mean size and a nice normal or Gaussian distribution where you know that one standard deviation out, that can be defined. You are between a set of sizes, two standard deviations out, you are between another set of sizes. So you can sort of say how many or what percentage of this material is likely to fall into a given size category. On the bottom, you don't have to have a normal distribution. It could be a distribution that is essentially single-ended, where you have larger numbers of very small materials and perhaps fewer numbers of large materials. So this is possible. You could also have the reverse. So they could be kind of standard, normal material distribution like the top, or they could be something, again, a little bit less normal. And still there is a distribution, and oftentimes that can be helpful to know and to work with. So let's try to do one of these grain problems. We're thinking about these granular materials. Again, they're kind of fluids, but they're not. They're really made of solids, but they can flow. So here we've got some grain. We're working on a building. It's got an 8-foot high wall. Okay, grain is placed into the storage building, and it is leveled to a certain height. It's within 6 inches of the top of the wall. So our height then is 8 feet minus the 6 inches. The grain density is 60 pounds per bushel. Could have been a different number, but there's a number. Lateral force per unit length at the base of the wall is most nearly, and then we've got some options. Okay, so again, we're going to use this P, pressure, equals LH squared over 2. So again, H is 8 feet, except it's really a little bit less than that, 7.5 feet, okay? And our L, okay, 60 pounds per bushel, but we're going to try to get that into pounds per cubic foot. So we do a little conversion there, keeping our units as we go across, bushels per cubic foot, pounds per, and then we end up with 24 pounds force per cubic foot. Now we've got that number to put in. We've got our H, it's now squared, divide by 2, and our pH is 675. Let's go back and see if we've got anything that is something like 675. We don't have 675, but we got 672. Okay, so when in doubt, when you have an answer that is close, go with the one that is most nearly that number. So it would be B to 672, since our answer was 675. You can check your math, check your units, make sure you've got those straight, just in case you had a different answer. Okay, but in this case, it should be B, 672. Let's try another sample question. If corn is treated, again, as a non-cohesive granular material, it's a flow type problem. The equivalent fluid density, pounds per cubic foot, is most nearly. Again, give us some options in pounds per cubic feet. Same thing, use our Hellervang. This time we need to look in the table. Okay, so we've got these different crops, all right? Equivalent fluid density, barley is 20, corn is 23, oats is 14, and of course we have others on that list. This is corn. It is 23, at least from what I can see on this. Again, which of these is most nearly? That would be A, 22. So hopefully you'll get exactly the answer, but if it's close and you've checked your work, pick the answer that is most nearly, the answer that is closest to the correct answer. And check and make sure. This is pounds per cubic foot. Our question said pounds per cubic foot. So we're all right. Okay? So again, don't worry about it if it's close, not quite there, but it is the closest answer. Okay? All right, let's take one more short break, and we'll come back and do just a little bit more before we're done. I think a break is a good call. So we'll see you in about 2 minutes. Okay, hi, can you hear me? Something. There we go. Thanks, guys. Sorry about that. All right, back to it. Let us do just a little bit more. We're going to back up, and I'll make some of those comments again. Sorry about that. All right, so we were talking here. Thank you. Water and biological materials. I did make some verbal comments about the question of assumptions that had been asked, and just said you need to state your assumptions. Yes, use your head unless you have a good reason to assume something other than the standard assumption. Go with the standard assumption. But if you are making an assumption and you realize that I could assume A or I could assume B, simply state what you're assuming. Write it down. In the cases where you're writing out a problem that is more of a writing problem, the grader can see that and can go with that assumption. So try to state your assumptions. That would be my suggestion. We are going to redo this. This is the moisture impacts in rheology. Again, the moisture content of materials can affect their physical properties, their stress strain characteristics. In this case, a piece of apple with different amounts of water in it, and also the rate at which forces are applied can affect how they respond. So again, we're going through some definitions. Wet basis, simply water mass divided by the total wet mass. The dry basis moisture content is not used as often, and it can get you some very different numbers. It's the water mass divided by the dry mass. So be careful about that. The AW is water activity, and this also is another way of measuring how much pressure, or it's basically a ratio of pressures. The pressure of moisture moving out of a known solution, probably something that's a solution of water with some sugar in it, over that same amount of pressure over pure water. So it's a ratio, and typically the high end is 1. If pure water would have a water activity of 1, but most other solutions are going to have lower water activities and will therefore have other aspects in terms of how they respond to moisture, but also how they might respond to bacteria. The relative humidity is simply the amount of water in a gas divided by maximum possible water at a given temperature. So temperature is very, very important for relative humidity. Warm air can hold much more water than cold air. And we will come back and see that in a psychrometrics section at the end. An equilibrium moisture content is the moisture content for some material. It could be a grain, could be any other biomaterial or food product, at a known relative humidity and a known temperature after a long period of time, T equals infinity, after it comes to equilibrium. And typically then it will get to a point where it will no longer absorb or desorb water at that relative humidity and temperature, and that is the equilibrium moisture content. And then we can put together curves of moisture contents and maybe even have hysteresis or nonlinearities in moisture content curves at different relative humidities and temperatures. So D245.5 addresses moisture relationships. Talks about moisture content on the wet basis. Again, this is sort of our standard, and that's simply the water mass divided by the water mass plus the mass of the dry matter. Okay, so you dry the thing, you find out how much moisture there was, which is the previous mass divided by or minus the amount that was lost. Okay, that's your WM. And the original is simply WM plus WD. That's on the bottom. Okay, so that's your sort of standard moisture content wet basis. Moisture content on a dry basis is a little different. It is WM divided by WD. And strangely enough, whereas the moisture content on a wet basis is somewhere between 0 and 100%, it can't be over 100%. The dry basis moisture content can be more than 100%, so to speak. It can be more than the number 1. If you have a fairly wet material, then the amount of water mass is greater than the amount of dry mass, so therefore the moisture content is greater than 1, greater than 100%. So it's a little bit weird. Dry basis moisture content, got to be careful of that. There's the definition. So to convert from dry basis to wet basis, we really simply have standard moisture content equals m over 1 plus m. And to convert back from the wet basis to the dry basis, big M equals little m over 1 minus m. So we can go back, let's look at these. Little m, our standard moisture content on a wet basis, is just Wm over the total mass, wet and dry. Big M is just moisture mass divided by dry mass. Okay, so now little m, that's our wet basis, our standard moisture content, is just big M over 1 plus big M. And big M, our less usual, our dry basis material, moisture content equals little m over 1 minus m. So pretty easy to tilt them back and forth. Might want to write those down, keep those in the back of your mind. Let's work an example. All right, so we've got some wheat. All right, we've got a pan that we're going to put the wheat in. It has a mass, all right, 10 grams. And the wheat, pour the wheat in there, and our new mass is 110 grams. Okay, so therefore and then we dry it. Put it in the oven, standard oven, 100 degrees C. Leave it for 24 hours or leave it until it gets to a standard dry basis. Doesn't change anymore. The dry weight is 100 grams. So the standard moisture content on wet basis, or the little m that we had before, is simply the water mass divided by the total mass. Well, what was our total mass? Our total mass, the pan plus the wheat's 110. Take the pan away, that's 10 grams. So we got 100 grams of wet wheat, so to speak. And how much moisture did we take out? Well, 110 minus 100, we took out 10 grams. So 10 grams of moisture taken out of 100 grams of original wheat. We got a 10% wet basis moisture content. That same material, same exact wheat, same exact process. Let's do the dry basis. How much water mass was it? It was 10 grams. How much dry mass was it? Oh, got to think about that. We had 100, we took away 10, so we must have 90 grams of dry mass. Okay, so 10 over 90, we've got 11% on a dry basis. So 10% on a wet basis, 11% on a dry basis. For relatively dry materials, not much error. I mean, there is an error, about a 10% error, but it's not bad. Let's look at a wetter material. All right, 10 grams wet, 3 grams dry. All right, now our wet basis, well, that means it's 70% moisture content. Okay, 77 grams, all right, out of 10 were water, 70% moisture content. But our dry basis now, 7 was the water, 3 was the dry material. So we have a 2.33 or a 233% dry basis moisture content. Very different from 70%. Now we've got a 200+% error. We got a huge error. So be careful, and especially be aware that wet materials, you have to be particularly careful. You will have a big error if you have a wet material. You've got to check, is it dry basis or is it wet basis? So just be careful on that. Pretty straightforward, but keep that in mind. Okay, isotherms are ways of looking at this equilibrium moisture content. So this is a series. Each one of these curves is several experiments that have been done at a known relative humidity, 70, 20, 30, 40, 50, 60, 70, 80, 90, maybe didn't get to 100% moisture content, but over some range, and then at a given set of temperatures. So at 0 degrees C, that upper curve, there were probably 6 or 8 tests run, each of which may have taken several days to allow, at that known relative humidity, at that known temperature, for this material to slowly get to its known equilibrium moisture content when it doesn't change anymore. And they plot these and they you can see that for a given humidity, typically things will be wetter. For a lower humidity, things tend to be drier. Makes sense. Interesting, as the temperature goes up, the equilibrium moisture content tends to be lower. Okay, you kind of know that. Heat's going to dry things out. Going to tend to, sort of move things down on that curve. And this is for a particular material. This is for yellow dent corn. And again, this comes out of the D245.5 standards, these isotherms. We can have water activity. Okay, again, water activity is the pressure above a solution or above this material divided by the water pressure above pure water. And here we have just a variety of materials. Again, dried milk, dried vegetables, chopped walnuts, dried potato flakes, crackers, cake mixes. These are things you think of as being, yeah, they're dry. Okay, water activity is low, 0.2, 0.3. Things that are sort of, yeah, a little bit wetter, you got some cheese, you got some molasses, dried figs, maybe they're 0.6, 0.7, 0.8, okay? And then things that you sort of think, these things could go bad pretty fast, sort of bakery goods, different kind of orange juice concentrate, and then things that will go bad relatively quickly, fresh meat, fruits, vegetables, sort of things that will rot. And they typically have a high water activity, 0.95, 0.9, 0.95, 1. Okay. High water activity typically correlates to lots of moisture and also correlates to the potential for bacterial issues. Okay. And then you can actually see on the right we've got different solutions. As we have more salt or more sugar, we will get a lower water activity. Okay, so once you get to about 19% salt, you're going to be at about a water activity of 0.7 to 0.8. Below that, as you have less salt, you will be 0.8, 0.9, 0.95. Okay, same with sugar. So again, just a feeling for these things. Very dry things have low water activity, often very good for, they can be dried and they can stay for a long time. They will probably not have a lot of bacterial activity. As you get to the higher water activities, these are the things that can go bad. There's more available water and things can grow in it. And again, we've got this relationship between the availability of water and living things or other activities that can happen. So way over at the left, this is water activity on the bottom. At low water activity, you don't have molds, yeast, bacteria. You really don't even have much enzyme activity, but you can have oxidation. Okay, oils can still go bad even at very low water activities. As you get to medium and then higher water activities, above 0.6, 0.7, you start to have things can grow on them. Molds, yeast, and then once you get to 0.8, 0.9, you can have bacteria that will also grow on them. That's when things will go bad fairly quickly. And so this is sort of a relation between that water activity and the activity of living things, molds, yeast, bacteria. Here's just one more kind of a close-up, a different example of, here again is corn, equilibrium moisture content on a wet basis. So this is your moisture content, and it could be between, at very warm temperatures and at low relative humidity, this material may be very dry, just a few percent. At a more typical relative humidity, that depending on where you are, if you're in a dry area, you might have typical relative humidities, 10, 20, 30%. If you're where I am in Louisiana, you can have typical relative humidities, 80, 90, 100%, okay? And then again, your typical temperatures. So up north, you guys are probably well below 40 degrees Fahrenheit right now. someplace perhaps out in the desert or something like that, you could indeed have temperatures 100 degrees Fahrenheit or more. And so those curves will reflect both the typical local relative humidity and the temperatures being applied. That's just a typical one. Thing that I wanted to point out here, very similar overall. This one is wheat at different temperatures. This is old time, 1939 data. Relative humidity versus moisture content. This material has been done. On the upper right, you can see mold growth. Data was not reliable. So even at about 80% relative humidity, you start to have microbial activity that will essentially be undesirable. So, I mean, one thing you're thinking about is you really don't want to go too high in the relative humidity or you will have undesirable activity. You'll not be able to keep that wheat very well. So some of that may be in your natural environment. It may not be much you have or can do with it. A lot of times you can. And you may well do some work to try to reduce the relative humidity within your storage material. Here's a little bit on hysteresis of these equivalent moisture content. So adsorption goes up one way, desorption comes down another way. And again, each dot on here is an actual separate experiment, okay, as they are adding and then taking away or gaining relative humidity and then reducing relative humidity. They follow slightly different curves. Over on the right, they actually follow fairly different curves. Kind of interesting. So there can be some hysteresis in these curves. And then different types of materials will have quite different shapes for their EMC curves. So how they take on moisture content. Dried peaches, as the moisture goes up, they get pretty wet. Okay, whereas something like wheat or cotton, at least until they get to 80–90%, they're going to stay fairly dry. So depending on the material, you'll have different EMC curves. And are there ways to estimate the moisture content based on other temperatures? So can we get some of these predictions to help us get some idea, maybe, for a particular material, what kind of moisture content we can expect? And again, perhaps to ask ourselves, have we designed this so that we will keep these materials in good shape? So here we've got an equation, 1 minus the relative humidity equals E to the minus KTM to the N. Okay, RH is relative humidity, just a percent or a decimal, 0 point something. The temperature is in absolute, degrees R. So keep that in mind. M is the equilibrium moisture content. That's going to be coming off these tables. K and N are constants, and we've got a little table here, different constants for different materials. We plug those in, and we can get an estimate of the relationship between moisture content and relative humidity. Okay, so sealed containers filled with soybeans at 20% moisture. Okay, so now we're putting materials in and closing it up. Now, a lot of times you'll do this. You think about closing a container, sealing up a food product. It may be a small container where you're simply enclosing in a plastic bag, or it may be something larger where you're closing in a bucket or a large structure even, and essentially locking it in, sealing it up. So you have this material, starts out at 20% moisture content on a wet basis. Estimate the relative humidity of the interseed air. And why does this matter? Remember, we want to stay below maybe 70 or 80% relative humidity to make sure that these are not going to degrade. And the temperature is 60 degrees. And then they give us some options. Fortunately, only one of these options is 85%, so hopefully we won't have that problem. So again, we can plug in here, put our relative humidity. We're plugging in our K and T that we got off that table. Temperature in Rankine. I make that connection, make that correction. So we start at Fahrenheit and then we go to Rankine. 20% wet basis, 0.0 0.2 wet basis, 0.25 dry basis. And that was what we had, isn't it? Oh, interesting. Dry basis. So the moisture content in dry basis. Be careful of that. So actually that is dry over wet is 20 over 80 or 25%. You won't be too far off, but you got to be careful there. To the 1.52. So again, what is our material? Soybeans. Let's go back to the table. Soybeans, K is 3.2 times 10 to the minus fifth. N is 1.52. So we bring those forwards, plug them in. K, 1.52, and 3.2 times 10 to the minus fifth. E2, that whole mess, so calculate that, e to the minus 1.962. 1 minus RH is 0.14, so the relative humidity is 0.86 or 86%. Now, what is that close to? 85%. Second question is, and you're perhaps not being asked here, but as a good design engineer, is that a good thing or not? And I think hopefully you're thinking, maybe not so great. You really don't want to be quite that wet. 85% moisture content, could have some biological activity in there. What can you do to deal with that? You may be able to put a food additive in that will be an adsorbent. So a lot of times you will find things that have a material in there that absorbs moisture out of the material to keep it dry. You could potentially do some kind of further drying before you put it in the container. Don't just dry it to 20%, try to dry it down to 15%. Run that calculation again and make sure that you get that relative humidity a bit lower. I don't know that you can do much about the temperature, but you could say store it at a certain temperature, and obviously changing that temperature will change the relative humidity. Actually, interestingly, if it's stored at a somewhat drier temperature, a somewhat higher temperature, that will tend to drive down the relative humidity. It doesn't change the total amount of moisture, but it will actually reduce the relative humidity. So kind of an interesting point there. Another aspect of moisture influencing the amount of material is the idea that as you add moisture, many substances will swell. You will have a specific volume change. Okay, and this is for a particular material. Moisture in pounds per 100 pounds of dry substance. So this is water over dry. This is dry basis moisture content across the bottom. Specific volume, cubic feet per pound of the dry substance, and then times 100. And it is a plot. As you get more moisture, you change specific volume. You actually have this stuff expanding. So one more thing to bear in mind. All right, I was going to wrap up with a section on psychrometrics. Psychrometrics is really the relationship between moisture, relative humidity, temperature, and the energy that's in the air and the moisture in the air. Okay, and a lot of times this is really important for the atmosphere in buildings, enclosed spaces. It could also be in enclosed spaces with agricultural material or food products. So how are you closing things in? A lot of times it will have to do with conditions in a greenhouse, conditions in a barn, conditions in some other enclosed space or building. So here's a very simple psychrometric chart. And what we have across the bottom is the standard temperature, dry bulb temperature. So this is sort of just normal temperature, in this case in degrees Fahrenheit, and then vapor pressure. So as the temperature goes up at a given relative humidity, vapor pressure, the vapor pressure will change. So at A, we're at 50% relative humidity. Now, if we simply hold that same amount of moisture and we simply heat things up, so we go from 70 degrees or just under 70 degrees at A and go over towards D to the right, we have we've simply warmed things up about 10 degrees. And what have we done? We've gone from 50% relative humidity to maybe 35%. So we we didn't change the amount of moisture in the air, but we ended up with less relative humidity. It actually feels drier. And that also means that you can dry things better. You can draw more moisture out of things. If we go from D up to B, what have we done? There we have changed, we've kept air temperature about the same, still about 80 degrees, but we have increased the relative humidity. And we have also increased the absolute moisture content, the vapor pressure. If we go from B back to C, now we have simply stayed at the same total vapor pressure. Total amount of moisture has not changed, but the temperature changes, and what happens to relative humidity? As we cool down, relative humidity goes up. And if we keep going across that curve, we'll hit 100%, and what happens at 100%? We get condensation. So on a cool night, as the temperature drops, if it's been fairly moist during the day, that temperature drops and it will hit a thing called the dew point. If it hits that temperature, you'll start to get condensation, dew, that comes on the grass. All right, here's a little more complicated psychrometric chart. This is a standard one out of Heatcraft. You can get them from other suppliers. And again, let's look at this thing. We have, on the left-hand side, we have enthalpy. In this case, it's English units, BTUs per pound of dry air. And that goes at an angle. And we've got, you can read it from the lower left, 15, 20, 25, 30, 35, 40. This is BTUs per pound of dry air. So this is actually a form of enthalpy, or essentially energy in the air. Then there's just a mark there that just simply says saturation temperature. And saturation temperature is the point at which the edge of this curve is. The curved edge, 35, 40, 45, 50, 55, 60, 65, 70. These are all degrees Fahrenheit. This is in English units. You can see that on the bottom we again have this dry bulb temperature. This is just like the temperature. If you simply put a thermometer out, starts at 35, 40, 45, 50, goes on up to 120 degrees. On the right-hand side, we have dew point temperature. And dew point is simply where that line intersects, and you can see that that should line up with the where the left-hand side of that curve, where we hit 100%, that is the dew point at that given amount of moisture. And then we have sensible heat ratio, okay, over on the right-hand side. And vapor pressure, that was what we had before, which is a way of measuring the amount of moisture in the air. And in this case, it's inches of mercury. That's a little bit different way, but basically it's the moisture in the air. So we're going to see if we can work a few problems. Psychrometrics is not as hard as it looks. Okay, so here's some suggestions to solve psychrometrics problems. Oftentimes maybe a greenhouse problem, could be an outdoor problem in terms of whether or not we're going to have dew, and that might affect how you manage an outdoor problem. Number one, read carefully. Think about, in the question, what stays constant. Then once you figure out what stays constant, get on a line and follow that line. Sometimes you have to interpolate. You know, you're halfway between something. You also got to read carefully. Okay. Sometimes you're going to have to make some calculations, do that interpretation. Okay. And then get to the end of that step. Okay. And then if you have to do another step, all right, then go and do the same thing again. Read carefully, figure out what stays constant, follow those lines, and eventually you'll get to the end. So let's just work on this a little bit. What stays constant? So going across, humidity stays constant. The total amount of water mass stays constant when you're going horizontal on this chart. All right. What line do I follow? Temperature, dry bulb temperature, that's at the bottom. Okay. And it's the vertical lines. Dry bulb temperature stays constant if you just simply go up and down the vertical lines. Wet bulb temperature, which is measured by literally putting a moist cloth over a sling psychrometer or a temperature measuring device and slinging it so that it cools off, okay? But it will only cool to such a point based on the amount of water that's already in the air. As that water comes off, it will cool that a little bit. If it's very dry, it'll cool it a lot. If it's very wet, it won't cool it at all. If it's 100%, so what you'll notice is that the wet bulb temperature, these are the ones that are a little bit of an angle, higher on the left, lower on the right, just a slight angle. If you look where it says wet bulb temperature and follow that to the upper left, you see 80 degrees. So that is the wet bulb temperature, 80. If you go straight down from that 80 at the top, what do you hit at the bottom? Dry bulb temperature of 80. So when it is 100% relative humidity, that's that far left curve, then you can't put any more water in the air. It's full. So you sling it around, but it doesn't cool off because no moisture evaporates. So wet bulb and dry bulb are the same at 100% humidity. Okay, so temperature could stay the same or could change. Saturation, okay, once we hit dew point, so let's go back and look at saturation. So saturation, you can see on the left-hand side, it simply says saturation temperature. That line is the 100% relative humidity line. It's a curve, okay? Curve from the lower left up to the kind of the middle of the chart. Makes a curve. That's the saturation temperature. When you hit saturation, if you go colder than that, you can't really fall off the chart, but what will happen to the moisture? Now you have too much moisture to fit in the air. If it gets colder than that, that moisture comes out as condensation. So you can kind of slide down the chart if you get too cold. Okay, humidity ratio, kilograms of water per kilogram of dry air. So humidity ratio, you can see on the right-hand side, there's a humidity ratio, pounds of moisture per pound of dry air, kilograms per kilogram of dry air, okay, or other options. So these are sort of the things. There's only a few things that can really change. Temperature can change, moisture content can change, or relative humidity can change. You can add or subtract some amount of water. After that, there's not really that much else that can change in psychrometrics. So here's an example, again, looking at something. The vertical line represents a constant dry bulb temperature. A warm temperature, I might add. Looks like we're almost 110, 109 degrees, something like that. The angled line shows a constant wet bulb temperature. And we note that if we add moisture, we will go straight up the chart. Start at 110 at the bottom, add moisture, and so our humidity ratio is going up. We're adding moisture, getting wetter and wetter and wetter and wetter, and then we follow the line. Once we get to a wet bulb temperature of 78 degrees, we then increase in relative humidity, 30, 40, 50, 60, 70, 80, 90, 100, and we hit the edge of the chart. If we attempt to go further, we're going to condense. So let's do an example. A day ends, it is 70% relative humidity, and it's 80 degrees Fahrenheit. So it's sort of a warm day. It's moderately humid, not super humid. But now the temperature drops to 70 degrees Fahrenheit. So first question is, what stays constant? Probably not the relative humidity, definitely not the temperature. So what does stay constant? Well, maybe the total moisture in the air, total moisture around should stay constant, at least for a while. Is there dew? And that question is, do we hit the left-hand side of the psychrometrics chart? And if there's dew, what is the dew point? The dew point will be the temperature at which that condensation just begins. That's the dew point. Or if we don't hit the edge of that, if we don't hit 100% relative humidity, what is the new relative humidity? Let's go back to our chart. Now we're focusing in on a little chunk of the chart. So here's 80 degrees. All right, remember, 80 degrees, 70% relative humidity. Then we're going to drop to 70 degrees. So 80 degrees, we go straight up till we find 70% relative humidity. And we didn't go far enough. That's 70% wet basis. We need to go a little higher to get 70% relative humidity. And then we are simply going to drop the temperature to 70 degrees. Presumably it doesn't change the moisture content, or the relative humidity rather. Doesn't change the total moisture in the air. So we simply slide directly sideways. And if that was the correct point, except that's more like 62% relative humidity, then we slide straight sideways. In that case, it looks like we're going to be 88% relative humidity. I'm going to just point out where we probably should be. All right, so we should follow up this line. And here's really 70, 80, 90, 100% relative humidity. So we really should have gone up this line to 70% relative humidity. Right? Did I get that right? 70% relative humidity at 80 degrees Fahrenheit. So 80 degrees Fahrenheit, yeah, 50, 60, 70%. This angled line is 70% relative humidity. Right straight up to 70, and then right straight across till we hit 70 degrees. Oh, now we're really close. Not quite at saturation, but we're really close. We're maybe at 99% relative humidity. Okay, if we really got that one right. So straight lines, a lot of straight lines. Do keep your eye on it. I got that one wrong. Sorry about that, guys. But very straightforward in terms of how you approach it. Let's do another one. A certain size greenhouse, 100 cubic meters, so pretty good size greenhouse. Temperature is 70 degrees Fahrenheit, relative humidity 40%, a little bit drier this time. How much water must be added to reach 50% relative humidity? Now, again, here's a good one for what are you assuming? If you're assuming there are plants in here, what are the plants doing? They are transpiring. They are probably adding water to the air. So you got to be a little careful here. But maybe this is a greenhouse that doesn't yet have. You're just preparing it for the plants. You're trying to get it to 50% relative humidity. How much water in the form of mist do you need to add to make sure you'll push this up to 50% relative humidity? And we got some assumptions here. Density of dry air, about 1/800th of water, 1.29 kilograms per cubic meter. And one more assumption, we're going to try to stay about 70 degrees Fahrenheit. Okay, state your assumption. Temperature remains constant. Density of dry air has a certain number. Okay, and we're simply going to add moisture to try to get from 40% relative humidity to 50%. Right? So let's try 70 degrees. All right, and we'll go up. There's our 40% relative humidity, 70 degrees. There it is. Okay. And we're going to try to get to 50%. So we're going to just go here, we get to 40, we're going to go to 50%. So how much have we added? This is 0.06, 0.07 something, 0.08, 0.09, 0.09 something. Okay, so we've added a couple, 0.02 maybe, 0.08, 0.01. So 0.002 we have added of moisture, okay? Difference is 0.002 pounds of water per pound of dry air, okay? So that's where we're at on those numbers. So that's how much we've added per pound. But we've got some different numbers to deal with, okay? 0.002 pounds of water per pound of dry air. But we've got this 100 cubic meter greenhouse. So we still need some kind of assumption there. So what is the mass of the dry air? Okay, and we had this assumption, 1.29 kilograms per cubic meter. Okay, about 129 kilograms of dry air. That amount of dry air times 0.002 kilograms of water per kilogram of dry air. That's what we're adding, remember? We're trying to add the 002. So that's how much physical water we have to add. 0.258 kilograms, all right, or 0.258 liters. Only around 1 cup of water. Just a little bit of fine misting will take us from 40% to 50% moisture content. So run the numbers, and what you do find is that, and this is kind of an intermediate, that's 70 degrees Fahrenheit, so just kind of like a normal temperature. We just need to add a little bit of water, a cup of water in a pretty large, 100 cubic meters, 10 times 10 times 10, you know, 30 feet by 30 feet by 30 feet tall. This is a good sized space. It may not be those particular dimensions, but 1 cup of water approximately will take us up 10% relative humidity. So it's a little bit of water, very, very fine mist, and then probably some evaporation should get us up. Okay, so I'm going to stop there with the psychrometrics, but hopefully that helps you. And again, you can come back and review this. It's being recorded. Come back and take a look at it. You're also welcome to write to me, shall5@lsu.edu, shall5@lsu.edu. Ask me a question, send me an email, I'll try to answer. But come back, review it, run your numbers. I was going to throw out a few more questions that you can ask as biological engineers that have to do with moisture, moisture movement, moisture and or temperature, air conditioning. So an air conditioning question oftentimes applies to humans. It could also apply to livestock, something like that, or even to storage of materials where you're trying to keep things at a certain temperature. A lot of times air conditioning removes water and also changes temperature. Why does it remove water? Because as the temperature drops, you're going to have water condensing. So a lot of times in a warm, humid climate, when you have an air conditioner, you'll also have some kind of drainage where that water moves out of it and you remove water from the air. You're essentially drying as well as chilling the air. Dehumidifying removes the water and maybe doesn't cool the air, maybe even heats the air just slightly. But a dehumidifier typically is something that removes water. It also removes the energy that's with that water. It could cool things, but a sort of ideal dehumidifier doesn't change the energy much, just simply removes the water. And again, could be for humans, could be for storage. You want to keep a certain environment dry enough that it's not too humid, not too wet. Rain would be something that can add water. Plant transpiration, that could be something inside a greenhouse that can add water. And so maybe you are watering with a spray or a mist or something like that, but once that water has been added to the plants themselves can push water into the air, especially in the daytime, making the inside of a greenhouse moist, but also, outdoors actually changing the local environment, making it more moist and simultaneously often cooling things because of the energy being released. The sun, meantime, adds energy. Things are going to get warmer. Oh yeah, the sun's coming out, it's driving off the mist, things are warming up. That means that the air can hold more moisture. Okay, and that will affect plants, could affect animals. Okay, at night we have essentially the opposite. We have radiation. Okay, we radiate to a cool night sky, especially if we have no clouds. A good clear night, we're going to lose a lot of temperature, radiating to outer space, very cold, and we are going to drop the temperature. That may mean we have condensation. If there's enough moisture in the air as it cools, we may hit that dew point and have condensation. How about drying process? So either you are trying to dry a material to avoid bacterial issue, or you are adding moisture in some cases. These could have a bacterial aspect, they could have a biomedical aspect, they could have a bioprocess aspect. Could be food related, could be health related, could be bacterial related, drying or adding moisture to get oftentimes to some kind of optimal or preferred moisture content for plant materials, food materials, or human materials. We're oftentimes doing some drying or adding moisture. So again, just a reminder on the psychrometrics, read it carefully, ask what stays constant. Simply follow those lines and then be very careful on how you do that and make your calculations. All right, in conclusion, remember your basic definitions. Be careful with units. I recommend you simply write down the units with every question, every part of every question. Cross them out if you have to, pounds per foot times feet per inch. Cross out the feet. Okay, fine, but write down the units that you are using. Use what you're given. Practice with your references. Get used to opening and closing your books, getting to the right spots. Keep a sense of time. So keep a timer and do that while you're doing your practice as well. And then keep learning. And then I would say right before, the day or so before the test, rest, relax, get comfortable, get a good night's sleep, eat a good breakfast, drink a cup of coffee if that's your thing, but get yourself there, comfortable, in time with your references, and then just focus on the exam, all right? I would suggest some other specific things with regard to material properties. Have any of these tables available to you. Any of these property references, and again, you can use the ones I've suggested. You can use others. Bring your favorites. Bring the ones you had in school, or bring the ones that you found that are very useful. You might even work your way through some of these as you're doing your practices. Some of them you're going to get mad at and throw it away. I'm not bringing that to the test. That's fine. If it's really not useful or if it doesn't work for you, don't use that one. Oh, but I really like this one. Then bring that one, mark it, know where the spots are to get to the references you need. Okay? And there's a lot of overlap between these different areas. So, thinking about the material properties will play into a lot of other mass transfer, energy related, biological, erosion related. There's a lot of overlap with these other areas. Wet bases, dry bases, we had that, little m, big M. Remember, they're quite different, and especially for wet materials, they can be very different. So again, keep an eye on definitions, write things down, and keep your head. Okay. So I'm going to stop at that point. I'll flip back, and if there's any more written questions, I'll stick around for a couple minutes. And again, if you want to write to me, shall5@lsu.edu. I have appreciated working with you. Hope that was helpful, and all the best on your tests. Thanks again.